The most important is the
Like the rent is so cheap in Germany.
Wait, we should not say that.
Yeah, it's
Yes, exactly.
it's called a salad.
Yes, exactly. You get it well.
Go there at 5 someone. At this guy. Corner towards the last from 1993.
and
So I think next year is Wi-Fi. Yeah. Alright. Yeah.
I know, next week is what Danny does for us. I have
you can't add. You need to add a contact first.
But when it turns around, it's...
Okay.
Take it off. So where is that? Yeah.
Yes, I think it is. I don't know how to turn it off.
What?
Can you hear? Can you see it? Can you see the presentation?
Yes, I can see the presentation inside.
Actually,
Next up, yeah. Okay, so just before we start, don't forget, those of you, HPC fellows who are visitors, make sure to go to this URL, please fill in as much detail as you can, the form there, and that let us set you up with accounts on the lab so that you can use machines over in the library. So please try to get today. So give me a shout if there's any problems or anything you're confused about. Let's try and get that sorted out so we can get your accounts on various systems here. And just to remind you, so because of this conference that's going on upstairs, and there'll be 500 librarians upstairs tomorrow, so very crowded, which is very quiet. We're going to move lectures tomorrow morning to the basement of the Lloyd building, and there's lecture theatre 1 down in the basement of that building. So you go in through the main doors, and you'll see right in front of you there's a set of stairs going down. So you just follow those stairs down, and I'll make sure I'm there to point you in the right direction for the right lecture theatre, starting at 10 o'clock tomorrow morning. So that way we'll keep out of this building here, which is going to be rather busy this week. So we'll be back here next week. So, lecture theatre 1 in the basement of this building tomorrow morning. Okay, so it's my pleasure to kick off the actual business of this meeting. And I'm going to give a few talks just about some numerical methods and think a little bit about how we might turn those into parallel codes along the way. So I thought, hopefully this is stuff, a lot of this stuff you've seen before. I'm going to work on an old bit of advice that I was given when I was a graduate student, which I'll pass on now to you, and that is whenever you give me a talk, always remember that the audience loves to hear stuff they know already. So I'm hoping that most of this list are things you've seen before, vaguely familiar with some of these ideas, some of the algorithms involved, how you might turn them into parallel code, and so we'll have a nice gentle introduction to the workshop before other speakers present more complicated stuff. So I'll start off thinking and reviewing again the sort of core, what most high-performance computers spend their time doing, which is solving problems in an algebra. So let's review that, and in particular we'll pick out two examples here. The Lanchas algorithm, which is a technique for finding the eigenvalues and eigenvectors, or some eigenvalues or some eigenvectors of sparse linear systems. And then, of course, hand in hand with that goes the conjugate gradient algorithm and more complicated derived algorithms that follow the same kind of path for solving linear systems. So we should review those just for completeness and pick out some nice examples, hopefully, of problems that we can solve using these techniques. Then again, let's look at a sort of a key, a very important numerical algorithm. Again, it's revolutionized scientific computing over the past 50 or 60 years. That's the fast Fourier transform. So let's look at the mathematics behind that, and again think about how we might translate that into a parallel code. So that's where we'll focus. And again, let's solve some problems and think of some applications. And then, depending how time goes, we can go and think about a favorite topic of mine, which is to think about Monte Carlo. Whether we get here or not will depend on how fast or slow I get. And I would encourage you to shout out if you're bored or if you have questions or anything like that, if there's anything that's very confusing, and make sure if you spot any typos on my slides, which I'm sure you will, then please do shout out, and we can spend some time reviewing topics. Okay. Sparse linear algebra. So hopefully this is stuff you've seen before in other workshops or in your undergraduate careers. Let's pick a problem to try and solve, just to make this concrete. And the problem we might try and solve is, can you hear the shape of a drum? So let's imagine we have some shape, a loop, a flat loop, on which we stretch some membrane. And then, of course, if we hit the membrane, it will oscillate, and it oscillates with a set of characteristic frequencies, a set of modes. And there's an infinite tower of those modes in general. And of course we have all sorts of different shapes in two dimensions, flat loops. And different loops will have different spectra. And so they'll make different noises. So the question we're asking now is, can you hear the shape of it? If I give you a spectrum of these eigenstates, these frequencies, the resonant frequencies at which the drum skin oscillates. And can you tell me the shape of the drum? If I was to hide it away behind the desk here, let's say, bang on the drum, and you had some device that could analyze the sound frequencies that were coming out, could you then infer the shape, without me showing you the drum, could you infer the shape of the drum? So if we try and put a slightly more mathematical spin on that question, then we can say there are the two distinct regions in 2 dimensions. Let's call them omega 1 and omega 2. And let's study the spectrum of the Laplace operator. There it is. On this domain, the angularity of this operator on this domain, with Dirichlet boundary conditions. So on the boundaries of this domain, the omega, let's set phi, this field, which is the displacement of our drum skin, let's set phi to 0 at the edges, so we're pinning our skin down on the edges, stuck it to this loop. And inside it can oscillate up and down. And the sort of equations of motion, if you like, govern, determine these oscillatory frequencies are basically, can we find the eigenvalues of this Laplace operator? So of course the way to solve any problem these days is to go to Google and type in can you hear the shape of the drum, and if you do that, get a Wikipedia page which tells the answer. So spoiler alert, the answer is yes. No, the answer is no. There's my first typo. The answer is yes to the question that I phrased inside that blue box. The answer is whether you can hear the shape of drums. So you can find two domains, and I've stolen this from Wikipedia, so you can look it up for yourself. This picture. You can find two shapes which are distinct, so there's no way I can rotate this shape into this shape here. It's a distinct shape. However, if I look at the spectrum of this operator on these two domains, and it turns out that the spectrum are identical. So in general, you wouldn't be able to hear the difference between these two resonant spectra for these two drums. So how will we solve this problem numerically? So there are sort of more robust proofs for this result, analytic proofs. But let's think about how we might solve this problem numerically. And what we need to do, of course, is we need to study the spectrum of this operator, and it's a linear operator, of course. And we want to study its spectrum, so we want to study the eigenvalues and eigenvectors of this operator. So what is our recipe for writing a piece of code that will determine at least some part of the spectrum of this linear operator on these domains? Now, of course, these in the real world, these spectra go on forever. There's an infinite town of state. So obviously, if we were to tackle this problem numerically, we'd have to truncate at some point. We'd have to stop at some point, and we'll come back to that. So maybe we should rephrase the question when we think about a numerical solution. Let's look at the low-lying spectrum, the lowest eigenvalues. How many of them we are particularly concerned with is a matter for experiment. So we need an algorithm, we need a recipe that will basically take an operator, a linear operator, and find its eigenvalues. Now, what we're going to do, of course, is we're going to try and discretize these domains. We're going to put down grid points and give values to the displacement of these drum skins at these grid points. And we're going to have lots of them. We want to have a good approximation. We're going to have lots of these grid points. So our representation of the linear operator, as we'll see in a slide's time, is going to be a matrix, which is going to be a big matrix. Maybe we want to put down a million points onto these drum skins and model the displacement of all of these points. So then this linear operator will be represented by a million matrix, a big matrix. So that really precludes the usual sort of traditional or old-fashioned numerical algorithms for finding eigenvalues of matrices that work very well for small, dense matrices. Here we have the opposite extreme. We have a large matrix, but what saves us, what allows us to make some progress, is that the matrix is sparse. So here we are, we're going to look at large, sparse linear systems. And the sort of starting point is to construct the Landshaw sequence. Who has heard of the Landshaw sequence? Okay, so only one hand has gone up. Okay, all right. So my starting point, my piece of advice that I should always tell the audience about something that they know is fallen down already, and we're already into uncharted territory, except for one lucky individual who can have a snooze. Okay, what's the Landshaw sequence? Okay, so first of all, the history. I should point out that Landshaw's Hungarian theoretical physicist. He spent about more than a decade in Dublin, actually, so there's some local history already. He worked at the Dublin Institute for Advanced Studies in the 1950s and 60s. So there's already a Dublin connection here to my slides. It's a recipe that takes a sparse linear system and represents it as a tridiagonal matrix. And then once we're representing this thing as a tridiagonal matrix, we can hopefully, these matrices are slightly simpler. It's slightly simpler to solve to study the eigenvalues and eigenvectors of these tridiagonal matrices. Now, what do I mean by a tridiagonal matrix? Okay, that's just a matrix where the only non-zero, so it's a very sparse matrix where the only non-zero entries are on the diagonal, and the two sub-leading diagonals above and below. That's what I mean by a tridiagonal matrix. We'll come back to some examples in a little while. Okay, so our problem is if we're going to try and find the eigenvalues of the Laplace operator to study the resonances, the resonant modes, the sounds our drum skin makes, we have to find eigenvalues of this Laplace operator. So first of all, we want to put down a grid of points on this on these domains, and then define a representation on that grid of the Laplace operator. And then once we've done that, we're going to use this Landshas sequence method to find the eigenvalues. Should I be concerned that it says Skype has stopped working? Okay, so the Laplace equation is our starting point. That's the differential operator this differential operator that I want to try to study. This is the Poisson equation in two dimensions. Here's our Laplace operator. It's a second order partial derivative with respect to x and y, the two orthogonal coordinates, as I move about my two-dimensional plane. So it's a rotationally symmetric operator, the simplest one, the simplest non-trivial scalar operator on this field. So now we want to construct a grid representation of this operator. So this is defined as a continuum, x is a continuous coordinate here. And so we want to restrict ourselves to just points, x and y points on the grid. And so hopefully you've seen this.
Okay, it's really
basically we're going to use the Taylor series. Our recipe is going to be to put down just a square grid onto our two-dimensional domain. And restrict this displacement of our drum skin to be defined only at these grid points. And at every grid point I will give the value for this displacement. So if I pick out a particular point and consider the value of its neighbour, one hop to the right, the next grid point, then I can define the value of that grid point as a Taylor series expansion in A, this lattice spacing, this grid spacing, the distance between neighbouring points. And the Taylor series looks as follows: it's equal to the value of this point plus derivative with respect to x, because I've displaced in the x direction, multiplied by the grid spacing, plus then an infinite tower of terms, each one higher and higher powers of this grid spacing A, and higher order derivatives as well. Now I'm trying to so now you see that here we're making link with the derivatives of the field by doing this expansion, by hopping around this grid, looking at nearest neighbours and comparing values at nearest neighbouring points. We can get information about derivatives, partial derivatives with respect to x by looking left and right, and partial derivatives with respect to y by looking north and south. And we're trying to construct a representation of this operator, but you see the dominant term, there are two dominant terms here at lower orders in A. So when A is small, these will be a bit bigger compared to this piece here, which is the piece we want to expose here. But you see there's a simple trick. First of all, we can just subtract this piece off directly because we have this value sitting in our computer. We know this number, it's stored in this array at this location. And we know this number, so you just take the difference between these two things, and that gets rid of this piece. But still we want to get rid of this first derivative, and we can do that by not only looking to the right, so not only comparing the data stored in our array here with its value to the right, but if we similarly replace A with minus A, essentially go to the left as well, and look at the data the other side, and then we can get rid of this term here, because this is obviously a sort of an odd function in x, in A, I'm sorry, and here we have even powers of it. So if I substitute A and minus A and add those two pieces together, I can cancel this piece off. So I can make a symmetric finite difference representation of this piece by just subtracting this piece off directly and then symmetrizing across those 2 points. And so with a few lines of algebra, not too tricky, you can represent our Poisson equation. So this piece here essentially is the representation of the Laplace operator, the thing we're trying to model to study our drum. And you can see all we have to do is add the two values, the two grid points to the left and right, and just up and down as well, north and south. So we add all of these 4 numbers together, and essentially we average them, and make a comparison with the value in the center. So now you see that, so we can represent our partial differential equation. Our linear differential operator can be represented in this way by just looking at the nearest neighbors around the grid point. So with these 5 pieces of data, we can approximate the Laplace operator. Everybody's happy so far? Good. And the result is the linear system. You see this is a linear equation, phi. Everywhere phi appears, it doesn't appear in any complicated function, it doesn't appear to any high power, there's no phi squared, there are square roots of phi, anything like that. This is a linear system, here a linear equation in terms of phi. If I have 2 solutions and I add them together, I get another solution. So we have a linear system. And it's also sparse. You can see if we have a million of these grid points, then at every grid point I have an equation, like this one. But rather than it being an equation in a million unknowns, it's an equation that just links 5 numbers together. So we have a sparse system here. If we write out this million by 1 million matrix, then there'll be lots and lots and lots and lots of zeros, and just a few non-zero. It's a sparse one system. And computationally, of course, what that means is that if we apply this operator, if we wanted to write a piece of code to apply this operator, we wouldn't directly store the matrix, we would just write a function that applies it to a vector. So we're never going to explicitly store this matrix represented as the coefficients that are representing connections between all of these values. So many of them would be 0 that it would be a very redundant thing to do. We would have wasted our computer's memory, because we'd be filling our computer's memory with zeros. And so there's a nice picture of it. You see that this is what's called a stencil for this linear operator, just represented by its 4 nearest neighbors. Okay, so now, having defined this operator, we'd like to study its spectrum, to find its eigenvalues. Now, if we have a square domain like this one here that I've drawn a picture of, then that's a fairly trivial exercise. The eigenvectors, if we have Dirichlet boundary data, are just the Fourier modes. But if we have a more complicated shape, then we have a more complicated problem of trying to find the eigenvectors of this operator. So in general, for more complicated shapes, the problem of finding eigenvectors is going to be a trickier one. For squares, it's a fairly trivial one. So we need a recipe, and our recipe is going to be the Lanchaussee. Somebody once told me how to say it properly, but I keep forgetting. The Hungarians in the audience who can tell us how to say the name correctly? Clio.
No, this was also wrong last year.
Okay. Oh, sorry, yes, Clio is a Russian mathematician now. Perhaps we have to remember somebody who can pronounce Clio. So this is an example of an algorithm. This is a Creel space method. So let's just quickly recap what that means. The recipe works just like conjugate gradient, which is an algorithm for solving these sparse linear systems, solving those equations, such as the Laplace or Poisson equation. Here we're trying to do a slightly different problem. We're trying to find eigenvalues and eigenvectors. Nevertheless, the mathematical foundation is the same. What our algorithm is going to do is it's going to construct more and more accurate representations of the operator in a subspace that is going to grow organically, iteratively. So it's going to start off with a one-dimensional subspace and try and construct an approximate solution in that one-dimensional subspace, then grow it to a two-dimensional subspace and try to make a better approximation, 3, 4, 5, and so on. And as the space grows and grows and grows, the approximation should improve, hopefully. And when M is a positive definite symmetric matrix, that you can prove that the approximation improves as you grow the Pillow space. So we're going to have an iterative scheme like conjugate gradient, which is going to grow this Pillow space, make it bigger and bigger, and construct an approximation, approximate eigenvectors and approximate eigenvalues inside this growing space. And these are recipes that work very nicely when we have these sparse linear systems, because to construct, so this vector space that we're going to construct, which is rank R, so dimension R, is spanned by a set of vectors, a sort of seed vector that we give, V. We're free to choose this vector V as a starting point for the iteration. And so it's spanned by the sort of vectors that are applied by, constructed by applying this operator to V, and then to the resulting vector, so applying it twice, and applying it 3 times, and applying it 4 times, and so on. So more and more times we apply this matrix, this linear operator, to our start vector, and that builds a vector space, which in general we have dimension R. And you can see that nowhere do I have to do anything except apply this matrix, this linear operator, onto vectors. Here we apply it twice. So there are no complicated operations on them at all, apart from just applying to vectors. Keep applying. So we just need to write a piece of code, or feed a piece of code into our black box, which all it does is it takes an input vector, applies this Laplace operator, or grid representation to it, and spits back out a new vector. And that's all we need to know about M, this matrix that we're trying to study. This is what's encoding our drum scheme, essentially. So nowhere do we have to shuffle around elements of this matrix. We don't have to do Gaussian elimination or anything like this. All we have to have is a recipe to apply the operator. And in doing so, what we construct is this Pillow space. And we can show that when M is positive and symmetric, then we have convergence. This algorithm will converge asymptotically. And it's basically an exact arithmetic when this vector space spans the full space of our problem. Count up the number of grid points to work out how big our problem is. And then we get convergence. But that's only true, of course, in exact arithmetic. And we're going to write a computer program which is going to use floating point representations of numbers. And so we're going to break this requirement, and round off we'll bring in a whole host of headaches for us, which we'll come back to. So in a world where our computers exactly stored floating point numbers, we would get convergence. But in the real world, we're going to have to struggle to maintain an algorithm that can cope, to some extent, with round-off problems. And that's what makes this algorithm tricky to turn to use in practice. Everybody still happy so far? Okay, but before I talk about the Lanchar sequence, let's backtrack and write down a recipe that would allow us to take one of these tridiagonal matrices and find its eigenvalues. And there's also, again, this fancy way of doing this, but here's a nice simple recipe that's easy to turn into code. It works reasonably well in practice.
No.
No?
I think we must post video on Cyprus.
Sorry? Oh, can you say that again?
We have lost the video.
Lost the video, okay. Somebody else's problem. Okay, so another sequence now. This is named after a French mathematician now, so we really are jumping around Europe. I think his name is on his, if you go to the Eiffel Tower, you can see his name on one of the corners of the Eiffel Tower, carved into the corners. 70 famous French engineers and mathematicians have their name on the Eiffel Tower, and his is one of them. So next time you're in Paris, you should look out for Sturm's name on the Eiffel Tower. Okay, so the Sturm sequence is the sequence of polynomials. Let's get back to what it is. But let's start off by thinking of the problem of finding the eigenvalues of a tridiagonal matrix. So here I've written the top corner of a tridiagonal matrix. Let's imagine it goes on for a long way. It could be a very large matrix. I've just written the top left-hand corner of it. And like I say, what I mean by tridiagonal is that the only non-zero entries in this matrix are the diagonal and the two leading subdiagonals. And I'm going to make this matrix symmetric as well, so you see the numbers that appear here, the same across, reflected across this diagonal. And so the task of finding the eigenvalues is basically solving this characteristic polynomial for the matrix, which I can write as the determinant of this matrix T minus some unknown coefficient lambda times the identity. And of course, the values of lambda that solve this characteristic polynomial when this determinant vanishes are the eigenvalues. So we're trying to find the roots of this polynomial. So the Sturm sequence is basically to imagine that we shrink the problem down, first of all, to a 1-by-1 matrix, whose coefficient is just alpha 0, is the first entry in this tridiagonal matrix. And so we can write down the characteristic polynomial of that 1-by-1 matrix. It's trivially just equal to this first order polynomial, which is just this coefficient in the top corner of our matrix, minus x. And I think all of us can find the root of this polynomial. It is, of course, alpha 0. And now let's consider a slightly, so that's the first order polynomial there. Let's consider a slightly bigger polynomial, a second order polynomial, which we will get by considering the 2-by-2 square matrix of those two non-zero. That's that little block, 2-by-2 block in the top left-hand corner again. Now it's a 2-by-2 matrix, and again we can still write down the determinant, write down a simple expression for the characteristic polynomial. It's just the product of these two diagonal pieces minus the product of the off-diagonal pieces, and has this form. And so now you see you have a quadratic equation you can quite easily solve for find the roots of this equation easy enough in terms of these three coefficients now, alpha 0 and alpha 1, the diagonal pieces, and beta 0. And the trick is now to recognize that if we keep growing these matrices, making them bigger and bigger, the problem of constructing these polynomials looks like it's going to get exponentially harder. But because it's a tridiagonal matrix, that's not true. The cost of constructing the next entry in this sequence, this is the Sturm sequence, the cost of finding the next entry is a constant in computer time, provided we've stored all the values of these polynomials. So applying these computing these polynomials for a particular value of x is only linear in this coefficient k, because we have this nice simple recursion relation. And so where does this recursion relation come from? Well, again, you see that if you were to compute the determinant of the 3-by-3 case, you have to expand out all of these terms in the determinant, but the only non-trivial terms we get are this term multiplied by the determinant of this 2-by-2 matrix, minus a term that we get by beta 1 times, another typo, that should be beta 1 over that, sorry. Beta 1 times itself times the determinant of this 1-by-1 matrix up in the top corner. And of course those determinants, if we're iterating down through this list, we've already computed. So P3, the characteristic polynomial, for a particular value of x, we can compute it if I told you the values of P1 and P2. So if we pre-compute P1, then compute P2, and then compute P3, it only costs us a few multiplications. Basically, you can see it's just this number times 2 minus this number. And that all holds all the way as you get as k grows and grows and grows. Because we always have zeros in all of these entries across here to the left of these two terms here, the only terms that appear are when I evaluate the determinant of the k by k matrix is the determinant of the k minus 1 matrix multiplied by the diagonal minus these two the off diagonal pieces times the determinant of the k minus 2 matrix. So now you see, generating the next entry in this sequence just costs order 1 in computer time. It's just a few multiplications and additions. It's a constant, it doesn't grow with k. And so evaluating the determinant of this characteristic polynomial is only order k in computer time. So that's nice and simple, nice and computer efficient. In general, evaluating the determinant of a matrix is a lot more expensive than that in general if the matrix was dense. And there's a nice result, proved by Stern. I'm not going to go through the proof here. Of course, if we, once this sequence gets all the way to the full size of the matrix, then this Pn is the characteristic polynomial that we need to solve to find the eigenvalues of the full system. So all of these intermediate results are not terribly interesting necessarily. We'll come back to them in a second. What we're trying to solve is the endpoint, Pn equals 0. That's equivalent to finding the eigenvalues of this matrix. So our endpoint is once we've filled out the entire matrix. But there's an interesting result regarding the roots of those intermediate polynomials that we construct. That's very useful for solving the problem of finding the roots of our polynomial at the end. So our exercise, our goal is now to find the eigenvalues of a tridiagonal matrix. Is to find the roots of the characteristic polynomial at the very end of this sequence. It's some complicated polynomial. We can't necessarily work out its coefficients very easily, but we can evaluate it for a particular value of x. And so we'll use some root finding method like bisection or something like that to find these roots. Bisection, of course, is a tricky recipe to implement because there's lots and lots of these roots, zeros, we're trying to find them all. We don't necessarily know where they are. Bisection, of course, needs to know a little region where one of those roots is guaranteed to sit. And this is the nice feature of this Stern sequence that actually makes this bisection algorithm work for this case. And there's a nice property, which I've tried to illustrate in this picture here. And it's basically, if we look at the roots, so we're trying to find these x values, if you like, if this was the number line, trying to find the location of these vertical stripes, which are the zeros of this polynomial P4. And there's a nice property which Stern proved, and that's basically that the roots of the polynomial with one smaller degree, P3 compared to P4, are always bracketed by the roots of P4. So here are the roots of P3 in this cartoon that I've drawn. Trying to find these eigenvalues, but what we're going to do is we're going to solve each one of these polynomials in turn. And that's going to give us, it seems like a redundant thing to do, we don't care where these stripes are, at the end we're going to throw away those values. But they give us very useful information on finding and solving the next problem part. Because what this cartoon tries to show is, and Stern proved this result, is that the roots of the n-1th size polynomial, so P3 compared to P4, are bracketed by the roots of P4. So if I knew the roots of P4, obviously I don't, then I can tell you that there's one root inside this region here for P3, correspondingly there's one root inside this region here. So you see there's always one stripe inside this band, one stripe inside this band, and so on. And the same is of course true all the way back down the sequence. That holds for P4 compared to P3 and so on. So if I look at the roots of P2, they can be bracketed by the roots of P3, so an upper pair of roots and another pair of roots. All the way right back down to P1, which is of course only got a single root because it's a first order polynomial equation. So So how do we use that in practice? So we want to solve this difficult problem here of finding the roots of this polynomial which is high order. What we do is we construct, first we solve the trivial problem here, which is finding the roots of this first order polynomial, so it's straightforward. And then we use that information to bracket the real line. At the moment we don't have any information about the lower bound of these eigenvalues. Sometimes we can get extra information about that. But at the moment that's not being determined. But we know there's going to be one root to the left at this point. So if I give you this point, I can tell you to go off and use your bisection solver to find a root in this domain. And you'll find one, exactly one. And also to look to the left and look to the right. So you'll find exactly one eigenvalue on either side of that. So that's a useful hint for you, to use a simple algorithm like bisection. And then correspondingly with those two numbers, you can use your bisection solver, look to the left at this point, there's one root there, look in between these two markers, and you'll find one root, and look to the right, and again you'll find one root. So you will construct solutions working down the page, and then you know at the very end you'll get all of the roots of the last polynomial. So it's a very robust recipe for finding all of the roots of this quite high order polynomial using quite a simple search recipe like bisection. So we haven't had to use any complicated information about these polynomials, their derivatives or anything like that. We haven't had to construct any difficult information at all. All we have to do is just apply them, and we're just using this sequence to apply them, and using this nice property of the roots of these intermediate polynomials. So again, easy to turn into code. Just to give you an example, let's just write down a 4x4 matrix. Here it is. You can check this very straightforwardly, hopefully. With your favorite package, Octave or MATLAB or whatever it is. So the characteristic polynomial P1 for the 1x1 matrix in the top corner, of course, it's just 5. It's just the value itself. And even by hand, you can check this case here. There's the eigenvalues of the 2x2 matrix sitting in this top corner are 1 and 6. And then you get messier, but there we are. That's just the way this matrix worked out. But again, you see this pattern. So 5 is somewhere is bracketed by 1 and 6. 1 is bracketed by 0.6 and 3.3. 6 is bracketed by 3.3 and 6.06. I mean, it's pretty close. I mean, it doesn't say anything about being in the middle or anything like that. So somewhere in that range, there's a root for the earlier polynomial. And so the job of writing a piece of code to solve iteratively, to construct all of these zeros, so these 4 numbers here, of course, are the 4 eigenvalues of this matrix, hopefully, unless I made a mistake. So these are the eigenvalues of that matrix, constructed following this very simple recipe. So there you are, a nice little homework exercise for you. You can write a piece of code, hopefully, either, like I said, using MATLAB or something like that, or write some C++ or whatever your favorite language is. It's quite simple to translate this into code and test it out on some of these little matrices. And you should check then to figure out what order your algorithm is as well in the end. If the matrix grows in size, how does your code slow down? So see if you can check that as well. And then is it numerically robust? So you can try with different matrices, see if it goes wrong. Okay, so that's given us a little recipe. Now, once we have a tridiagonal matrix like this one here we now have a recipe for finding its eigenvalues. And it's a reasonably, another.
Skype has stopped working again. Just
Yeah.
That's not a problem.
Let's do it.
Yeah, okay.
The video is recorded. I'll send the video later.
Is it just a network connection? Keep dropping it down?
Yeah.
Yeah. Can we try and find a wire connection? We need a wire connection.
Better.
for tomorrow.
Yeah. Okay. I'll try and use that. Yeah. Right. Okay. Okay. So now we have a recipe. If I give you a tridiagonal matrix, then you can use this trick to write a 20-line piece of code to find its eigenvalues. But first of all, I haven't told you yet how to actually construct this tridiagonal representation of our operators. So we want to go back to our original problem of finding the nodes of this operator on our drum skin. First of all, we need to take this operator and translate it into this tridiagonal form. and that's going to be done through the Landshut algorithm. So here I've written out just a recipe that you could, sort of pseudocode style recipe that you can translate reasonably easily into code. Let's have a quick look at it before we understand how it works mathematically. Just from a structural point of view, you see that it's, perhaps it looks a bit messy up on the screen there, but it's simple to translate into code. Because all we have is the only place the matrix, our drum skin appears, if you like, the shape of our drum appears is in this matrix M, and all we have to do is just apply this linear operator to vectors. So the only place M appears is just acting on vectors. So perfect for sparse linear systems. And as well as that, we just have, we have to just add vectors together. It's an easy operation, obviously enough. And we have to take dot products as well. And so we can think about translating that into code, which we'll do soon. That's hopefully going to be something that's straightforward to do. Once we have written a kernel that will evaluate dot products and apply this linear operator. So once we have those bits of code written, then this is a nice, simple workflow built up from those Lego blocks, if you like. And so again, thinking ahead to how we might write a parallel code, there's no hard MPI to be done with this stuff. There's no sort of complicated communications beyond the stuff that's hidden inside, evaluating dot products and applying operators and doing linear combinations of vectors. So once we've solved the MPI coding problem of applying this operator to a vector, and there's a global reduction problem of computing dot products. Once we've sort of locked down those pieces of MPI code, we've got them right, then implementing this in software is a fairly straightforward task. And you see as well, of course, it's this cross space method, it's an iterate method. So we're going to construct these sequences, but happily the storage doesn't grow with the well, okay, if you want the eigenvalues, it does. Okay, so maybe you should be more careful. Sorry, if you want the eigenvectors, it does. But we can actually overwrite the computer's memory as we go along here as well. Because we're just referring back to the previous entries. K minus 1 and K minus 2 are the only indices that appear in this here. So if we were just interested in computing eigenvalues, we're going to have to come back to this problem of round off, which will kill us a little bit and spoil this nice picture. In a perfect world where we didn't have floating point representation and round-off problems, then our memory footprint for this code, even though we're constructing this sequence of vectors, so it looks like we're storing lots and lots of vectors in our computer's memory, we can overwrite that memory because the only indices we refer to are K minus 1 and K minus 2. So on paper, at least, before we worry about floating point representations, it's a very neat and compact memory footprint for this algorithm as well. And so let's just quickly skim through the steps now, and I'll show you how it's working to construct this tridiagonal matrix. So you see that these numbers, alpha and beta, with indices on them, it's alpha 0, alpha 1, alpha 2, so on, and beta 0, beta 1, so on and so forth. And those really are the entries in this in this tridiagonal matrix. The alphas are really going to be the diagonal elements of this matrix, and the betas the leading off diagonal elements as well. Once I get rid of my typo, those will be the same either side of the axis. And I just have these little temporaries here, which I have to introduce just to keep the arithmetic sane. So what I do is I just apply the operator and I subtract this alpha, which is this coefficient here. And this alpha is chosen essentially to ensure that T1 and V0 are orthogonal. So I'm going to construct this sequence of vectors and they're going to be mutually orthogonal. If I wanted that, then I have this free parameter alpha. If I choose it to take this value, then T1 is orthogonal to V0, whatever I V0 is anything I choose. Then I can do this beta, which is just the modulus of this vector, and I rescale to make V1 just the appropriate amount, rescale value of T1 such that V1.V1 is equal to 1. So now it's a unit length vector, if you like, a unit modulus vector. So that's what this step is here. And this coefficient beta, it turns out there's an off-diagonal piece in the tridiagonal matrix. We'll see that in a second. And then we go again, we construct a new alpha. Again, it's just a dot product of the previous vector with n applied onto it. And now I take this linear combination here, and I have to look back one more step to look up one of these betas and subtract off vk minus 2, subtract off some amount of vk minus 1, and to construct this next entry in the krill. Grow the krill space here, you see we've applied n one more time. Construct this temporary vector. And this recursion ensures that tk is orthogonal to all of the previous v's. So that's the magic of this recipe, essentially, and you can prove that relatively straightforwardly. I'll show you the next slide. And then again, this last pair of lines here is just rescaling t, this temporary vector, so that v has got modulus 1. Again, rescaling it so under the 2 norm, it's modulus 1. vk.vk is equal to 1. So this is the clever bit is encoded in this line of the recipe here, and that's sufficient, you can show, to make sure that vi.vj for any different elements of I and j are orthogonal and symmetric. Well, of course, vj, vi. So they form the columns of an orthogonal matrix. And that orthogonal matrix is starts off with a single vector and it's growing horizontally as we increase the sequence. And again, if you just, you should sit down and convince yourself, it doesn't take very long to convince yourself that this recipe ensures that this orthogonality condition holds. And here's the most complicated part of that proof is looking at the orthogonality relation. We start off with V0, then look at V1 and construct V1 and V2. Then let's look at V0.T2, just writing it out. Well, by construction, this is already 0. This is equal to 1, so this is just beta 0. And now you see we choose beta 0 so that this thing cancels this. So we see that this cancels against this because of this nice result here, where I can basically rely on this, the symmetric property of the matrix M. So I'm assuming that M is symmetric, so that here I can flip around this expression here. I can apply M to the left, and write this expression backwards, and then use the recursion to write out M acting on V0 in terms of V0 and V1, and then we see again that we just pick up beta 0 in this bracket, and we get this nice cancellation. So it's worth just looking and convincing yourself that that works. The trick is, the assumption we've used is that M is symmetric, so that we can write this expression backwards. Instead of applying the operator to the right, we're going to apply it to the left, and that gives us this result here. And so that's just starting things off, looking at V0 against V1 and so on and so forth, looking at the start of this sequence. But that's enough then to construct following exactly that same reasoning, we can construct an induction that shows that orthogonality relationship holds. And so if we're doing that orthogonality, we know that the sequence has to terminate at least at k equals n. Maybe it could terminate earlier. And now we can rewrite this expression again. This is the sequence right now again, just multiplying out betas. And we see that then basically M acting on this matrix, where I've filled in the columns of this matrix by these V's, M acting on that matrix can be written as M acting on any one of these rows, any one of these columns, gives me a linear combination of the VKs with one index smaller and one index bigger. And I can always just write this then as a linear combination. Putting the linear combination to the right, it's linear combinations of columns, and all of these entries a long way away from the diagonal are all 0. And so now you see, of course, we've represented the matrix M as this tridiagonal matrix. It's a similarity transformation that we constructed that writes down this tridiagonal representation for M. Everybody see that trick? So we've, more formally, these are now matrices. I've written NV equals V. And now we've gone all the way to the we constructed the full sequence at this point, assuming these are square matrices. And of course, because B is orthogonal, it's easy to construct its inverse. Its inverse is just a transpose, and now you see we have this represented similarity transformation that relates M to this tridiagonal matrix. If I find the spectrum of M, I can find the spectrum of T, and those two things should be equivalent. Nice. So that's the Landschaft sequence then. Takes this intermediate step, takes this arbitrary symmetric operator, constructs a tridiagonal representation of it that we can then easily find the eigenvalues of. Okay, so I'm going to finish up there. Everybody happy enough with that? Everybody okay with that? So there's one little homework exercise just to make sure you understand the step sequence. Why don't you try and see if you can just solve this problem here inside the box as a starting point, and then look at some more complicated ones. Make your code flexible enough to deal with bigger matrices. See if you can write a Stern sequencer. And then if you fancy a nice project, here's a nice thing that would take you a lot longer. This is a few weeks coding exercise. In fact, you can get it done in 3 weeks. I don't know. That's how good you are writing it. Let's see if we can solve this problem. Can we hear the shape of a drum? Can we find eigenvalues for these shapes? Why don't we try and write a code that uses this Landschaft algorithm to find some of the lowest eigenvalues? How many we can get is an open question. I haven't tried this myself. Restricted to drums that are made of these triangles and squares fused together, like those pictures that I got from Wikipedia. Like these pictures here. So let's restrict ourselves to these sort of shapes. Let's try and do arbitrary code, because that would be a very tricky exercise. But if we were to, already this is, these two apparently have the same spectrum, so this is already an interesting case to look at. Let's imagine that we have just shapes that are made of little right triangles, that are half a square triangle sort of thing, or squares. So you can see both these shapes I can get by gluing together squares and little half triangles. So if we restricted ourselves to that case, could we write a code that would compute the eigenvalues, the resonant frequencies of our drum skin, made up of these triangles and squares stuck together? So how many eigenvectors can you get? Can you find they match up for those for the case that's given on the Wikipedia page? Do they line up? Can you reproduce this result? And could you write an MPI code that then would where each MPI call gets either one of these squares or a little triangular subsection to deal with, and where we have to obviously then think about how we would translate this into code tomorrow. We'd obviously have to then exchange data between these MPI calls. When you write a bit of code that computes dot products, and when you write a bit of code that applies the Laplace operator on these domains. So that's an interesting problem. Can you solve this HPC borrow problem?
Sorry, are we going to have access to the slides?
Yes, somehow. How are we going to do that? Yeah. Short answer is yes. I can stick it up on the web page just now. Yeah, we do that.
Yeah, we complete in the HPC website, or you can send it individually, whatever you choose. It's going to be free, available, or it's going to be available to students.
Let me, in 5 minutes I can stick it up on the web page. Let me just give you a URL and then we can also post on it. Let me give you a URL. It doesn't exist at the minute, but I will go and dump the slides. It's URL as quick as I can get back to my office. Okay. So this is a tilde, of course. www.maths.tcd.ie /MJP put in this directory here. MJ.
M like Milan. M.
M like Mike. It's my name. HPC. Okay, so it doesn't exist. I don't try looking at it. You'll get a 404 and you can go there now, but I will go and sort it out for you in a second. Okay, good. So I think, according to the timetable, there's a
half an hour break, Greg. I guess it's up to you if you want to start now. If you can break it.
No.
All right, I'll see you tomorrow. So don't forget, tomorrow at 10 o'clock, Tony Kennedy's starting to tell us about symplectic integrators, and that lecture will be in the basement of the Lloyd building. Lecture theatre ones are not here tomorrow. Move away from the librarians, we'll go down into the basement, which hopefully will be a bit less busy, hopefully, and we'll be there for the rest of the week. Okay, good.
Okay, we're going to take like a 5-minute break, and then until I plan my computer, you can go to the toilet. Yeah. So, thank you so much.
Somebody knows how to work with this.
Yes, he's very man. He's well trained. He's been doing it for
Yeah, I guess we should maybe think about trying to get a mic.
yeah, maybe Skype is not so helpful. Maybe we use Google Photos. It seems like to be more robust than Skype.
Okay, well, we can.
We'll
talk tomorrow.
Nevertheless, we record.
Yes.
So the recording is robust and it's okay. We're gonna, have it in the portal.
Yes.
So please ask the.
I will send it.
Okay, I just sent an email now to get in contact with Theo, which is currently in Cyprus, just so you make this presentation more comfortable. Because people in Cyprus.
I'll email the slides to you now and then. So you don't copy anyway, but I'll put it up there.
Same way I'm going to copy the HPC website.
Perfect.
Not too bad, yeah. So we can go out on like Friday.
Yeah. Really easier.
Yeah, we'll avoid the choice sizes as well. Yeah, I think
Does your microphone charge? Does it have charge? Can I use it?
Oh, yeah, that's the system one.
Yeah.
No need to. You will be recording this as well.
Yeah.
But on a separate file.
Oh, okay.
And I should have it. I will decide whether to use it or not.
No, it's the same file.
Huh?
It is the same file.
No.
I'm not removing it.
Stop the recording and then look, if it's the same file, then I have to be strict. Do you want me to be strict? Do you want me to follow with Monte Carlo? If you want, I can follow with Monte Carlo. What?
I had
I don't think that you want another side.
I can record also this one. Are we recording this, right?
Yes, but in a separate file.
Oh, okay.
Okay, so stop.